Hello everyone. In this lecture, I shall discuss the numerical solution of differential equation. Basically, here I will discuss some standard methods such as the Taylor series method, Pickard's method, Euler's method, Runge-Kutta method of order 2 and 4, etc. Now, coming to the many problems in science and engineering, it can be modeled by using the differential equations, right? We know different techniques to solve the differential equations, but it is not always possible to find the analytical solution in closed form. Okay, all such differential equations cannot be solved by the usual technique. For example, the complicated situations like the ballistic missiles, the satellite theory, the vibration theory, bending of beam, electric network, electric circuits, etc. Okay, here the differential equations are formed and we do not have a analytical solution, so we use the numerical solution to overcome the such difficult cases. Okay, basically here we will discuss the solution of first order differential equations and under given condition known as the initial conditions. Okay, so IVP, first order IVP. Subsequently, this can also be extended to the system of equations as well as to higher order equations. We consider a first order differential equation of the form maybe f x y dash equal to 0. It is in implicit form, and if we write it explicitly, it is dy by dx is f of xy in explicit form with the given initial condition y of x0 is equal to y0. And various numerical methods are known such as the Taylor series method, the Pickard's method, Euler's method, modified Euler's method, improved Euler method, Runge-Kutta method, etc. So these methods are single step methods. Okay, these methods are single step method. Single step method because we just use the previous step to find the outcome of the subsequent step. Okay, so these are the single step method. However, we have the other methods such as the Adams best fourth method and the Adams Moulton method, etc. So these are here multi-step method. Multi-step method. Multi-step method means we may use the outcome of previous step and several steps also to have a subsequent calculations. Okay, now as we are talking about the solution of the differential equation dy by dx is equal to fxy, y of x0 is equal to y0, we must know the sufficient conditions for the existence criterion of the differential equation. The existence criterion, and it is under the Lipschitz conditions. Okay, you are given a differential equations as in equation number 1. We say the solution is unique and the solutions exists if fxy is defined and continuous in the strip x0 less than x less than b, horizontal strip, and the vertical strip minus infinity to infinity. Here we are given the initial point x0 and we subsequently go on increasing up to b. You are asked to find the solution in the interval x0 and b. Here x0 and b are finite. Okay, and basically the second condition is our Lipschitz condition. F of xy minus f xy1 is less than some constant times y minus y1. Right? Here y and y1 are any two real numbers. However, if you see this Lipschitz condition is a weaker condition then the assumption that f of y is continuous and bounded. Okay, the condition 2 can be replaced by this. However, condition 2 is better, it is a weaker conditions. Okay, so before we have the details of discussion, let me to introduce myself Professor Susanta Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Visut, Burla, Sambalpur, Odisha, India. So without much delay, let us discuss the different methods one by one. Now let us discuss the Taylor series method. the Taylor series method. You are given a differential equation of this form, the initial value problem, first order differential equation, and here in order to apply the Taylor series method, we should have the function f(x, y) must be sufficiently differentiable, right, with respect to x and y. Now the solution of this differential equation y of x can be obtained by using the Taylor series expansion about x0, right, and the Taylor series expansion about x0 is of the form y of x is equal to y of x0 plus x minus x0 y dash x0 plus x minus x0 whole square by factorial 2 f double your y double dash x0 plus x minus x0 whole cube by factorial 3 y triple dash x0, and so on, it is continued. So now you see that this is a function of x, right, this is y of x, it is a function of x. So at a different value of x we will find y of x, the solution, at different points within the given interval. Okay, the interval may be given that I is your x0b, means we start from x0, we continue up to b with a step length of h, means here xi is equal to x0 plus ih, equispaced. Okay, x0 plus ih, equispaced. So what we do, we find y of x, basically it is a function of x, and where here y of x0 is given, y of x0 is equal to y0, this is given, right, and what is your y dash is equal to f of xy. Subsequently we find y double dash. What is y double dash? We have to use the implicit differentiation, right, implicit differentiation means you have here f of x plus f of y, again differentiated with respect to y by chain rule, dy by dx, means it is fx plus fy into f. And similarly we find y triple dash, means we have the implicit differentiation, means use implicit differentiation and find y dash, y triple dash, etc. at given x, at x0, or we can say at x0 or given x, right, at x0 or at given x. Now this implicit differentiation also called the total derivative of fxy. We may call it the total derivative of fxy. Okay, and use implicit differentiation, find this, then find y at desired x. For simplicity we just apply the Taylor series formula, and with this use the given initial conditions, y of x0 is y0, you substitute here y0, and subsequently you find y dash x0, y double dash x0, y triple dash x0, so on up to the desired accuracy as it is asked, and you just substitute here for a particular value of x desired, and you find the solution. Now to have a feeling of numerical solutions, what we will do, to have a feeling of your numerical solutions, right, to have a feeling of iterating scheme, let you put your x minus x0 is equal to h, right, you put x minus x0 is equal to h. So that means your x is equal to x0 plus h. x0 plus h means x0 and with a small increment in h, and it is my x1. So consequently this formula becomes my y of y of x0 plus h. Okay, y of x0 plus h is my y of x1, and it will be my y0 plus h y dash 0, it is y0 plus h y dash 0 means y dash x0 plus h square by factorial 2 y double dash x0 and so on so on so on hn by factorial n yn x0, right, and plus the remainder term, or I can say the epsilon and the remaining term, the error term, remainder term. Okay, so next you for your x2, okay, you have here y of x2, y of x2 will be y1 is obtained here, it will be y1 plus h, it is actually here y dash 0. So now here it is for y of x2, it is y1 plus h y dash x1 plus h square by factorial 2 y double dash x1 and so on you continue it, and we may write a formula, it is here plus hn by factorial n yn x1, right, plus epsilon n is my error. You see now what is my y dash is fxy, is not it, so it will be my f dash xy, right, and it will be my f n minus 1th derivative xy, right. So consequently I can write it, if I continue like this, I write here y of xn or yn plus 1 is y of xn plus 1 will be yn plus, I may take some h common here I may write it, suppose fn, I write it fn, so it is fn xn yn. You see for x2 it is x1, for n plus 1 it is n, okay, plus already one h taken common, h by 2 here fn dash xn yn, you continue, right, and it is continue like this, and it will be my hn by n factorial, it becomes 1h is taken common, hn minus 1 by factorial n, it is fn minus 1 derivative at xn yn plus the remainder term, next term will be here hn plus 1 by n plus 1 factorial, because this h is here, again we have h to the power n, it is f nth derivative at xn yn, or we may replace it, I may replace it by some point say zeta, with this zeta lies in between xn and xn plus h. Okay, now this term is my error term, here this fn can also be replaced by yn plus 1, right, this fn can be replaced by yn plus 1. Now if I denote this as my capital fn xn yn, we will have our formula is here yn plus 1 is equal to here yn plus h fn yn, here n greater than is equal to 0. So this is the Taylor series formula with here error en or epsilon n is equal to h to the power n plus 1 by factorial n plus 1 y n plus 1th derivative at the point zeta, some zeta lies in between xn and xn plus h. Okay, so this is a formula, right, this is the formula for the Taylor series expansion, right. So here there is a feeling like the numerical methods. However, we don't need it. We just find yx by using this formula, which is a function of x, and I substitute different value of x to get the desired solution in the interval x0 and b, and the quotient should be there, right? This yx what we find, it should be in the neighborhood of x0, right? It should not far away from x0, and your h should be sufficiently small, right? H should be sufficiently small. Here h is sufficiently small, right? As you see, this h should be, then your error is less. Okay, this should be the idea. So if we move in this way, rather it will be little bit complicated, right? Complicated in the sense that first we find here y of x0 is y0 given. We find y dash is equal to fxy, right? And we find y double dash. By implicit differentiation, we find y triple dash, okay? And at x0 we compute these values. Then we find y of x1, right? Then we recalculate. Then again we recalculate here y dash, y double dash, y triple dash at so on at your x1. Then subsequently you find y of x2, right? And we go on proceed to get the answer. Okay, so we may move like this. Otherwise, as I have told, just we write this formula, express it as a function of x. At different x, we compute the solution, right? So this is rather than easy. This is easy approach, and we can have this approach, and this will be complicated. So let us solve some examples, then your idea will clear. Basically here we have discussed the solution for first order initial value problem. However, this can be extended to higher order differential equations, subsequently also for system of differential equations. So now as I have told that this method can also be extended to second and higher order differential equations as well as for the system of differential equations. Now coming to the solved example 1, we are given a differential equation, right? We have to find y of 0.1, y of 0.2. First we have to write y of x up to 6 terms, okay? So coming to the solutions, it is straightforward. Coming to the solution, here y0 is equal to y of 0 is 1 and x0 is here 0. This is y0, this is y0, and this is here x0. Now y dash is here fxy is here xy plus 1, So this implies what is my y dash 0, y dash at the point 0. So this implies here y dash 0. What is y dash 0? It is x0, y0 plus 1. x0 is here 0, y0 is here 1. So it is 0 plus 1 is here 1. Okay. Then you find y double dash, the implicit differentiation. Apply the product formula here. X derivative of y plus y into derivative of x is 1. So now you find y double dash 0. Y double dash 0 means here x0 and here y dash 0, right? Y dash 0 plus y0. So y dash 0 is this is your y dash 0. So x0 is 0, y dash 0 is 1 plus y0 is your 1. This is equal to your 1. Then you find y triple dash, the derivative of this product formula. Here x y double dash plus y dash into 1 plus here this is y dash. So this is equal to xy double dash plus 2y dash. Okay. Then you find here y triple dash 0. Y triple dash 0 is x0 y double dash 0 plus 2y dash 0. You substitute it, x0 is here 0, into y double dash 0 is here 1 plus 2 into y dash 0 is here 1 is here 2. And likewise you find y fourth derivative, it will be your x y triple dash plus 3y double dash, and it will be y fourth derivative at 0 is here 3. Similarly you find y fifth derivative, it is xy fourth derivative plus 4y triple derivative, and y fifth derivative at 0 is here 4, okay, etc. And since we need 6 terms, so fifth derivative will give you 6 terms because the first term is free from the derivative. So now by Taylor series, now using Taylor series expansion, we have y of x is equal to y of x0 plus x minus x0 y dash x0 plus x minus x0 square by factorial 2 y double dash x0, and we continue, it is x minus x0 to the power 5 by 5 factorial y of fifth derivative at x0. So here y0 is 1 given and x0 is given 0. So substituting this, simplifying this, I am getting 1 plus x, the value of y dash 0, y dash 0 is 1. Then next will be x square by factorial 2. Next will be x cube by factorial 3 plus, here you see, here y dash 0 here is, y dash 0 here is here 1, and y double dash 0 here is here 1, and y triple dash 0 here is here 2, plus x fourth by 4 factorial, y fourth derivative is here 3, right, plus here x5 by 5 factorial, fifth derivative is 4, okay. So simplifying, it is here 1 plus x square by 2 plus x cube by 3 plus x4 by 8 plus x5 by 30 up to sixth term, okay, and it may be continued here, but we are writing up to the sixth term, right, up to the sixth term. So subsequently we have we are asked to find y at the point 0.1 and y at the point 0.2. So what is my y? Now y at the point, now my y at the point 0.1, I substitute x is equal to 0.1, x is equal to 0.1, so it will be my 1 plus 0.1 plus 0.01 by 2, then x cube is 0.001 by 3 plus 0.0001 by 8 plus 0.00001 by 30, and if I simplify it, it will be up to the fourth term, it will be my 1.1053, and accordingly my y of 0.2 will be, I substitute x is equal to 0.2 here, 1 plus 0.2 plus 0.04 by 2 plus 0.008 by 8 plus 0.0016 by 8 plus 0.00032 divided by 30. If I simplify it, it will give me 1.22122, and which is my up to fourth term, it will be my 1.2212, right. So up to 4 decimal places, clear. So here we directly substitute, x is 0.1 here, x is 0. If I want to think of the iterative scheme, we can apply y of x1 alternatively. Y of x1 is equal to y of 0 plus h y dash 0, here x0 plus y double dash x0 h square by factorial 2, like this, and here h means it is given in the interval, it is in the interval 0, 0.2 I want to solve, okay, with here spacing h is 0.1, so that here 0.1, then here 0.2, right. So if you think like iterative scheme, then it will be, so we substitute the value of x0 here. Okay, here x0 is equal to 0, h is equal to 0.1, and I calculate it, it will give me 1.1053. And similarly here I can apply, alternatively I can apply y of x2 is equal to y of x1 plus h y dash x1 plus h square by factorial 2 y double dash x1, right, and I continue. So here what is here x1? x1 is equal to here 0.1 I substitute, h is equal to 0.1 I substitute. So I have to recalculate the derivative here. I have to recalculate here what is my y dash 0.1, what is my y dash 0.2, and likewise, and I need to substitute all these values here, and it will give me, if I simplify, it will give me 1.2212. Okay, so you direct substitute the value of x, getting a formula for the Taylor series of this form, or we may have a iterative scheme. Now in example 2 we solve a second order differential equation. Okay, so here the condition is x0 is here 0 here, x0 is here 0 here, x0 is 0 and y0 is, this is y0, this is your y0 is 1, y0 is 1, and this is your y dash 0, y dash 0 is here 0.1. Okay, so the necessary formula is the Taylor series expansion. Taylor series expansion is given by y of x is equal to y of x0 plus x minus x0 y dash x0 plus x minus x0 square by factorial 2 y double dash x0, and so on. So now let us compute. We are given what? So now you let, this is my y double dash plus 3x y dash minus 6y is equal to 0. Right, if you differentiate it with respect to x, so it is actually 3x y dash, it is plus 3x y dash. Now if you simply differentiate it, implicit differentiation, it is y triple dash plus 3, you have here product formula, x derivative of y dash is y double dash plus derivative of x is 1, it is y dash into 1, and minus 6y dash, right, this is equal to 0. If you again differentiate it, it will give you y fourth derivative plus 3 into xy triple dash plus y double dash minus 6y double dash is equal to 0, right. So this means y fourth derivative plus 3x y triple dash plus, so this is equal to 0, this is equal to here 0. Now if you again differentiate it, it will give you y fifth derivative plus the product formula here 3x into y fourth derivative plus y third derivative into 1. Okay, this is equal to 0. Now consequently I find what is my y double dash 0. So my y double dash 0 is equal to, that means at my x0, okay, at my x0 it is y double dash x0 plus 3 x0 y dash x0 minus 6 y of x0 equal to 0. I substitute the value, x0 is my 0, y0 is 1, so that means y double dash 0 plus 3 x0 is my 0 and my y0 is 1, y0 my 1, minus 6 y0 is your 1 equal to 0. So that means y double dash 0 is my 6, y double dash 0 is 6. I substitute again at x0, I compute y double dash 0 here. Okay, so I find y triple dash 0 here, y triple dash 0 will be 0.3. Similarly I find y fourth derivative at 0, y fourth 0, if I compute y fourth 0, it will be my minus 3 x0 y triple dash 0. x0 is 0, so this is equal to my 0, and I compute it here, means my y fifth derivative at 0, it will be my minus 0.9. Now I substitute all this result here. So therefore yx is equal to, thus at x0 is equal to 0, here y of x is equal to y0 plus x y dash 0 plus x square by factorial 2y double dash 0 plus x cube by factorial 3y triple dash 0 plus x fourth by factorial 4y fourth derivative at 0 plus x5 by factorial 5y fifth derivative at 0. I just substitute the value of y0 is 0.1, value of y0 is 1, value of y0 is 1, it is here 1, plus x into value of y dash 0 is 0.1 plus x square by 2 into y double dash 0, we get it, it is my 6, plus x cube by 3 factorial y triple dash 0 is my 0.3 plus 0 plus x5 by 5 factorial y fifth derivative is minus 0.9. If I simplify it, it will be 1 plus x by 10 plus 3x square plus x cube by 20 minus 3x5 by 400. Okay, so you are asked that what is y of 0.2. So now y of 0.2, simply I find, put x is equal to 0.2. Okay, if I put x is equal to 0.2, it will be my 1.1404. This is my answer. Now coming to the third example, you have to obtain the Taylor series as a power series in the power of x minus 4 and solve this equation 5xy dash plus y square minus 2 is equal to 0 with the initial condition y0 is 1, x0 is 4. Okay, and subsequently we need to find y.1, 4.1 at 4.2, 4.3. Okay, so it is in the neighborhood of 4, not far away from 4, right? So this should be the basic principle. Now coming to the solution, the Taylor series is given by Taylor series in power of x minus 4 is given by yx is equal to y of x0 plus x minus x0 y dash x0 plus x minus x0 square by factorial 2 y double dash x0 and so on. Now this is x0 is 4, it is y of 4 plus x minus 4 y dash 4 plus x minus 4 whole square by factorial 2 y double dash 4, it is in the power of x minus 4. Now we need to, y0 is given here. Now we consider the differential equation. Consider the differential equation. Here 5x y dash plus y square minus 2 is equal to 0 with y0 is equal to 1, x0 is equal to 4. We find y dash 4. So that means my 5x0 y dash 0 plus y0 square minus 2 is equal to 0. You substitute x0 and y0. So that means 5 into 4 into your y dash 0 plus y0 square 1 square minus 2 is equal to 0. So that means y dash 0 or y dash x0 we find here is equal to your y dash 4 is equal to your 1 by 20. Now if you differentiate it, then we need to find y double dash 0. If you differentiate it, it will be 5xy double dash plus y dash into 1 plus derivative of y square 2y into y dash. Okay, so this is equal to 0. And you simplify it, implies 5x0 y double dash x0 plus y dash 0 plus 2y0 y dash 0 is equal to 0, and if you simplify it you will get y double dash x0 is y double dash 4 is equal to minus 0.0175. Now suppose considering this 2, we have up to the third term, the Taylor series expansion is, now the Taylor series up to third term will be here yx is equal to 1 plus y0 plus here x minus 4 into y dash 0 plus x minus 4 square by factorial to y double dash 0, and if you substitute all this thing it is 1 plus x minus 4 into y dash 0, we got it 1 by 20 is here 0.05, it is 0.05 plus x minus 4 square by factorial 2, and it is here y double dash 0 is minus 0.0175. Consequently, we find here y of 4.1, y of 4.2, y of 4.3. Just replace x as 4.1. It will be here 1.0049. It will be here 1.0097. It will be here 1.0142. So in this way we will find the solution up to 4 decimal places. So now the thing is that we use Taylor series method to solve first order as well as second order also. In the same way it can be applied to the system of simultaneous equations. So now at this stage, if we feel this lecture is useful and interesting, please like and subscribe to this channel, which will boost my motivation to upload the subsequent lectures. One more thing, the video is getting lengthy because in one lecture we try to incorporate so many examples of various aspects. Okay, so you should go through this lecture. Let us close these lectures. Thank you all. Have a nice day.